Have you ever looked up at the vast, star-dusted canopy of the night sky and wondered where it all came from? It's a question that has captivated humanity for millennia, a puzzle at the core of our curiosity. The night sky appears serene, unchanging, a silent theater of distant lights. Yet, the story of our universe is anything but calm. It is a dynamic, dramatic tale of unimaginable energy, breathtaking expansion, and the slow, patient emergence of everything we see and know. Scientists call this origin story the Big Bang. The term can mislead. It wasn't an explosion in space. It was the beginning of space and time. Grasping this idea challenges everyday intuition. Exploring the Big Bang expands our perspective to a cosmic scale. Galaxies, stars, planets, even us, from the simplest beginnings. The atoms in your body were forged in ancient stars, themselves born from material created moments after the Big Bang. So, what happened before the Big Bang? It's a natural question that almost everyone asks. We think in cause and effect, in a before and an after. But the theory posits time itself began with that event. Asking before is like asking what's north of the North Pole. The Big Bang is the starting line for the cosmic clock. Physics works from a fraction of a second onward, but breaks down at the initial instant. At the singularity, density and temperature go infinite. Our equations cease to make sense. Scientists explore string theory and quantum gravity to unite the very large with the very small. Ideas like multiverses or cycles are fascinating but speculative. So we begin at the first describable moment, just after the beginning. From there, evidence guides us through rapid expansion that set the stage for everything to come. At the very beginning, in the first fleeting moments, all the energy, all the matter, and all of space itself was compressed smaller than an atom. It was incomprehensibly hot and dense. Gravity, electromagnetism, strong and weak forces likely unified as one. A perfect, seething soup of pure energy. Then, it happened. The universe began to expand, not into space, but as space itself. Like raisins in rising dough, distances grow because the dough, space, is expanding. In a tiny fraction of a second, inflation swelled the universe from subatomic size to larger than a grapefruit, faster than light. Space can do that. Expansion cooled everything, and the unified force froze out into the distinct forces we observe today. As the universe expanded and cooled, it crossed critical thresholds. Within the first microsecond, energy condensed into quarks and gluons, a quark-gluon plasma. Today, the Large Hadron Collider recreates glimpses of that state by smashing heavy ions. By 1 second, quarks bound into threes, protons and neutrons, the cores of atomic nuclei. The cosmos was an opaque fog, electrons, particles, and a blinding bath of photons. Light scattered constantly, unable to travel far. Between 1 and 3 minutes, it cooled enough for fusion. Big Bang nucleosynthesis. Protons fused with neutrons, making deuterium and helium-4 with traces of lithium. After 20 minutes, fusion stopped, yielding 75% hydrogen and 25% helium by mass. Telescopes see the predicted hydrogen-helium ratios, a stunning confirmation of the model. The basic chemical ingredients of the cosmos were set. Next, the universe would cool enough for atoms to form and light to break free. For the next 380,000 years, the universe expanded and cooled, but remained an opaque plasma. Photons were trapped, constantly bumping into free electrons, like headlights in dense fog. At 380,000 years, temperatures reached 3,000 °C, a magic threshold. Hydrogen and helium nuclei captured electrons, forming stable, neutral atoms. Recombination. Instantly, the fog cleared. For the first time, light streamed across space. That ancient light is the cosmic microwave background, the oldest light in the universe. With atoms formed, the fiery era ended and the cosmic dark ages began. No stars, no galaxies, just neutral gas. But it wasn't perfectly uniform. Tiny fluctuations, seeds from inflation, were there, ready to grow. These seeds would, over eons, become the scaffolding of cosmic structure. Gravity would soon end the darkness and light the cosmos once more. Within dark clouds of hydrogen and helium, gravity, weak yet relentless, went to work. Slightly denser regions pulled in more matter, the rich getting richer. Over millions of years, a vast web of filaments and sheets took shape. At intersections, gas piled up, forming the first proto-galaxies. Clumps collapsed, core temperatures climbed into the millions. Eventually, fusion ignited. The first stars were born, ending the cosmic dark ages. Their ultraviolet light re-ionized hydrogen, making the universe transparent and luminous again. These first stars were giants, burning fast, dying young as supernovae. Explosions seeded space with heavier elements, the raw material for later stars and rocky planets. Small proto-galaxies merged into larger ones, billions of years of ongoing construction. Our Milky Way, a spiral galaxy with hundreds of billions of stars, formed within this grand process. How can we be so confident about an ancient, hot, dense beginning? The universe left clues, most powerfully, the afterglow of the Big Bang. When the universe became transparent, ancient light was released, the cosmic microwave background, or CMB, a faint, nearly uniform glow bathing the entire sky. In 1965, Arno Penzias and Robert Wilson found a persistent hiss, residual heat from creation. Satellites, COBE, WMAP, Planck, mapped the CMB in exquisite detail. They found tiny temperature fluctuations, 1 part in 100,000, the seeds of structure. Those ripples mark density variations that gravity later sculpted into galaxies and clusters. Predicted as red-shifted thermal radiation, measured at about 2.7 K, exactly as expected. A powerful testament to predictive science and a snapshot of the infant universe. When we detect the CMB, we're seeing the faint glow from the dawn of creation. Another pillar of evidence comes from galaxy motions, Hubble's discovery in the 1920s. He found nearly all visible galaxies moving away, the farther the faster. This linear relation is Hubble's law, the signature of expansion. Like raisins in rising dough, distances grow because space stretches. There is no cosmic center. Every observer sees others recede. Rewinding yields an age of about 13.8 billion years and a hot, dense beginning, the Big Bang. Together, CMB, expansion, and primordial element abundances form a tripod of evidence. Even with a quality amateur telescope, perhaps from a trusted brand like AstroTube, you can see galaxies whose light traveled billions of years. Each photon is a message from the past. Recap: the universe began extremely hot and dense and has expanded and cooled ever since. Expansion is space stretching, not an explosion into emptiness. In minutes, hydrogen and helium nuclei formed. At 380,000 years, atoms formed and ancient light broke free, the CMB. Over billions of years, gravity assembled stars and galaxies. Observations confirm this picture end to end. We still don't know what dark matter is. Dark energy drives accelerated expansion. Its nature remains mysterious. What ignited the Big Bang, or what came before, is beyond present physics. 13.8 billion years later, we find ourselves able to look back and understand. From simplest beginnings, staggering complexity arose. Galaxies, stars, planets, and life. As we gaze up, we see not just points of light, but the unfolding history of the cosmos.